Okay. See, good morning, good afternoon to one and all. In the previous lecture, we have discussed regarding characteristics of DC motor. In that, we have concluded all the characteristics like torque versus armature current characteristics of DC motor. Again, we have seen regarding torque versus speed characteristics, that is speed torque characteristics, and also we have discussed regarding the characteristics is that the speed versus armature current characteristics, that is T versus IA characteristics, speed versus armature current characteristics, and the torque versus speed characteristics. So these three characteristics of all types of motor we have already derived, like characteristics for shunt motor we have derived the characteristics for DC series motor. Also we have derived the characteristics for DC compound motor. Okay. I think there is no problem in the characteristics. Is there anyone having any problem in the characteristics? Please give me reply. कोणाला काय प्रॉब्लेम आहे का कॅरेक्टरिस्टिक्स मध्ये?
No, sir.
Okay. So see, we will discuss today the next one point is that the losses in the DC motor and the losses and the concept of efficiency. After that, we will discuss the condition for getting an maximum efficiency in case of DC motor. DC motor ची condition त्याच्यानंतर बघणार आहोत आपण. To get the maximum efficiency, at what condition the efficiency of the DC motor it will be maximum. See, before discussing that, we will discuss the losses in case of DC machine or DC motor. As similar to that of DC generator, there are some of the losses due to that of rotational part, due to that of winding resistance is there, also due to that of some manufacturing magnetic property of the material. Okay, see, since DC motor is machine, it must have some losses during its operation. Okay, so see, DC motor it is an one rotating machine, so that it is having and some of the losses, it is having and some of the losses it will be present during its operation. While operating a DC motor, it is having and some of the losses because some rotation part is there, there are some of the friction is there, or it may be bearing is there, so that there are some mechanical losses it will be present. It will contain again some of the resistive part, so that due to that resistance there are some of the copper losses is there. Also this machine it will include some of the magnetic property material like a core, or it may be pole show, so that there are some of the losses related to magnetic, that means iron loss and hysteresis losses. So like that, due to its operation there are some of the losses it will be present. And as the current flows through the armature winding and the field winding, there are certain copper losses. Okay, see, the armature winding and field winding having and some of the resistance, armature winding and the field winding it is having and some of the resistance, so that armature and field, due to that armature and field winding it is having and some of the copper losses. त्याच्यामध्ये काहीतरी काय असतील copper losses असतील. Okay, see, since the current it will be alter its direction, current it will be alter its direction. So if the current it can be altering its direction, again there are some of the losses like hysteresis as well as ED current losses. Hysteresis loss or it may be ED current losses are there in the armature core. So we call the hysteresis and ED current loss collectively as a core loss. Okay, so this hysteresis and ED current losses which are comes under core losses, so that we can call it as a core losses, or we can call it as a constant losses also. त्याला आपण constant losses पण म्हणतो, as well as we can call it as a core losses machine. Okay, see, we call the hysteresis and ED current loss collectively as a core loss or the magnetic loss. Now the DC motor is dynamic machine, that means it will be having and some of the rotating part, so it is a dynamic machine, hence there is a frictional loss in the bearing. So due to the rotational force, there are some of the rotating mechanism is there, like bearing it will be required for the smooth operation. If the rough bearing it can be used, then the operation of the machine it will be rough operation. Okay, so see, if the operation of this rotating part it will be rough, then there is a losses like a friction loss is there. त्याच्यामध्ये friction loss, that means it will provide some of the opposition to that of rotation. So there is a friction loss. Hence, the friction loss in the bearing, it is also one of the mechanical loss. And for the same reason, there is a windage loss in the air gap. So again, in the air gap between stator and rotor, in the air gap between the stator and rotor, there is a windage loss is there. Okay, again there is a windage loss is there in the air gap between the stator and rotor. Stator and rotor च्या air gap मध्ये काय असते? Windage losses असते. Okay, so see, these are the some of the losses. Both the frictional and winding windage losses are the mechanical losses. जे frictional losses आहेत and these are the some of the windage losses are comes under frictional loss, or we can call it as it is the mechanical losses of the machine. ते machine चे काय आहे? Mechanical losses आहे. Okay, so these are the comes under the mechanical losses of the machine. Mechanical losses of the machine. Okay, see, these losses, some of the losses due to the magnetic winding, or it may be core, so that we can call it as a core losses. Second one type of losses is nothing but due to the current flowing in the resistive coil, like armature coil, or it may be a field coil. There are some of the copper losses, it will be present in the form of heat. Again, there are some of the mechanical part is present in the DC motor, or the mechanical part it will be present in case of DC motor. So that there are some of the mechanical losses like as a friction and windage losses is there. Friction and windage losses is there. Okay, there is a friction and windage losses is there. So these are the some of the losses it will be occurs in case of DC motor. DC motor मध्ये या टाइपचे losses काय होतात? Occur होतात. We will see in the details regarding that losses, which types of losses it will be occurring in case of DC machine. We will see. See, due to the resistive part, just 1 minute. See, due to the resistive part of the machine, due to the resistive part of the machine, or it may be there is some of the resistance of the winding, or it may be resistance of the armature winding or copper winding, it will contain a copper losses. Copper losses, as we know that the copper losses, it is nothing but it is the proportional to the square of the current. That means I square R losses is nothing but we can call it as a copper loss. So see, these types of losses it will be occur in the these types of losses it will be occurs in the armature copper loss or a field copper loss. Armature copper loss or field copper loss, it will becomes under the copper loss. Next one type of losses is nothing but iron loss. So generally we can call it as the iron loss is nothing but core losses. It will be happen due to the magnetic property of the machine. So it is the magnetic manufacturing property, so that we can consider these losses, it is constant losses, like hysteresis loss, or it may be ED current loss. Hysteresis loss or ED current loss. And then last one types of losses is nothing but mechanical losses. In mechanical losses, so these losses it will be occur due to the mechanical part of the machine. So in case of mechanical losses, it will be like as a friction loss, or it may be windage loss. Okay, so these are the some types of losses it will be occur in case of DC motor. So see, we will see one by one these types of losses. And the mechanical power developed in case of DC motor. Do you know that the DC motor, there are some of the mechanical power it can be developed in case of DC motor. As we know that we have derived the voltage equation, and also we have derived the power. We have already discussed regarding power stages in case of DC generator. So similarly, the mechanical power PM is nothing but power developed in the armature. Then V into I, it is nothing but input power to that of motor. So it is the A stage in case of motor. V into I, it is nothing but input power. PM is nothing but B stage, it is nothing but mechanical power, and the power developed in the armature of the machine. And again, actual output of the machine or output of the shaft, it is nothing but the output actual. So it is nothing but C type of power. Okay, see, the PM is nothing but, that means this mechanical power, it is nothing but input power V into I minus, due to the field winding and the armature winding, which are the copper losses, it will be occur. Okay, so that means I square R loss. I square R loss, if it is minus from V into I, we get the mechanical power developed. And do you know that the EB equation, that is terminal voltage V minus V divided by 2, it is equals to V by 2 is nothing but EB, or we can call it as a back EMF. Okay, it is nothing but back EMF. See, these are the power flow in case of DC motor. These are the power flow in case of DC motor, or this is the power flow diagram. Do you know that the DC motor, it is an electromechanical device which can convert the electrical energy into mechanical energy. कशामधून कशामध्ये कन्वर्ट करतं? Electrical to mechanical or mechanical to electrical?
Electrical to mechanical.
Electrical to mechanical. That means input of the motor, it is in the form of electrical, and the output of the motor, it is in the form of mechanical, right? No. So in between that electrical to mechanical, there are some of the losses it will be occur. So firstly, I think you people know the generator power stage. So similarly, the reverse of that, it is nothing but motor power stage. Power stages to that of motor. See, electrical power input is nothing but P into P in, that is input power fed to that of motor, that is P in. After that, the copper losses, that is PCU, and the PB. Okay, PCU, that is copper loss, because it is having an some of the resistors. Due to that resistance, the I square R, it is nothing but copper losses. After that, we got some of the power developed in the armature. So power developed in the armature, we can represent either it is EB into IA, or we can represent EA into IA. So it is the power developed in the armature. So here represented PD. Okay, PD is nothing but power developed. After power developed in the armature, the motor rotor, it will be start rotating. Again, there are some of the frictional losses, or it may be windage losses, that is mechanical losses. So see here it is given these losses due to the rotational losses, and these losses are comes under the fixed, and this is the output power of the motor, and it will be get at the shaft of the machine. Output or power at the shaft, we can call it as the output power of the motor. Okay, so these are the power flow diagram, or the power flow in case of DC motor. Power flow in case of DC motor. Now see, we will see details the losses, how these losses it will be occur, what is the reason behind it, or what is the reason behind that losses. So we will see that. That is, first one is nothing but we have seen, that is copper loss. So copper loss, it will be found in all the winding of the machine. So machine winding, it is having and some of the resistance. Machine चे जे काय winding असतील किंवा motor चे winding असतील, so it is having and some of the resistance. It is having and some of the resistance. So due to that resistance, if the current flowing from that winding, so this resistance, it will oppose to that current. So somewhat the heat or power, it will be dissipate in that resistive part. The resistive part मध्ये somewhat power काय will dissipate will in the form of copper loss, that is I square R loss, and it is depends upon I square. By convention, they are computed using the DC resistance of the winding at 75 degrees Celsius. Okay, so for our convention, we are computing this copper loss when the machine it will be running and the winding resistance, or winding temperature, if it is increases up to 75 degrees Celsius, then we are calculating resistance. I think we have not taken Swinburne test. In case of Swinburne test, we want to I think we have taken no Swinburne test concluded no Swinburne test घेतली का आपण practical?
Yes, sir.
हाँ, in
Yes.
case of Swinburne test we have measured resistance, right? No, आपण resistance measure केला होता.
Yes, sir.
So this resistance we have already measured when we are operating the machine. Machine operate करून झाल्यानंतर आपण hot condition ला resistance measured करतोय. That means at that situation when the machine it will be operating somewhat normal condition, at that situation some temperature of that winding it will be increases, and we want to take the value of resistance at that temperature. That means we are computing the value of resistance at somewhat that temperature, that is we have calculated armature resistance. The actual resistance depends upon the operating frequency and the flux condition. Okay, so जो काही actual resistance असेल that we have calculated or computed while the temperature of the machine it is nothing but 75 degrees Celsius or below to that. So this resistance it will be depends upon the operating frequency, at which frequency we are operating that machine, and what are the flux condition. So depending upon that we are calculating the resistance of the machine or motor. Any difference between the actual and computed copper loss is as counted for under the stray loss category. If there is a difference between the actual resistance and the computed value of resistance, or it may be somewhat there is a change in between the actual value of resistance and the computed value of resistance, so that the copper losses it can be counted as a stray loss, or it will be counted in the stray loss category. So do you know that stray losses in case of generator it is depends upon rotation. If the frequency and flux, if there is a minimum frequency, or it may be there is a maximum flux, then the speed of the machine it will be low. If the minimum flux is there, the speed of the machine it will be high. According to equation, n is directly proportional to EB divided by phi. If the phi is greater, then speed is less. If the phi is less, the speed is greater. So if the flux is greater, that means speed is less. So at a somewhat less speed, the loss, or it may be heat of generated in the machine, it will be less. Okay, so that somewhat the resistance calculated and computed, there is some of the difference. This difference it is due to the stray losses, and it is depends upon rotation. Stray losses कशावरती depends असतं, rotation of the motor याच्यावरती depends असतील. So it will be depends upon some motor rotation. Okay, motor rotation. Now next one types of losses is nothing but brush loss. As we know that the brush DC motor it is having one of the slip ring. On that slip ring there are some of the brushes are placed. त्याच्यावरती brush काय केलेले असतात, press केलेले असतात. So it is nothing but we have seen in case of construction the brushes are pressed against the slip ring. In case of DC generator it will collect a current from the armature, and in case of DC motor it is used to fed the current fed करण्यासाठी use करतात. That means to give the supply to that of winding. Okay, see, in case of brush there is again due to that of rotation there is some friction between brushes and slip ring, right? No, brush आणि slip ring च्या मध्ये काय असेल, काहीतरी friction असेल. So due to that frictional, or due to the friction, there is some of the brush losses is there. So brush losses, two types of brush are commonly used in case of DC machine. One type of brushes it can be used graphite type, that is carbon type of graphite, and another one we can call it as a metal graphite. In either case the brushes have resistance and will thus dissipate a power. Okay, so brush, it is having an some of the resistance. I think in commutation process, instead of using carbon brushes, we are using the copper brushes. Sorry, instead of using copper brushes, we are using the carbon brushes because we are increasing the resistance, right now. So this is the one solution we have seen, that is resistance commutation. Resistance commutation मध्ये आपण काय करतोय, instead of using that type of brush, we are using another types of brush to increase the resistance. So if the resistance it can be increased, then the that means sparkless commutation it will be achieved. This is one of the remedies we have already covered. So see, if the resistance of that brush it will be increases, if the resistance increases, it will carry a current. That means again power dissipation it will be increases, right? No, त्याच्यामधलं power dissipation काय होईल, due to that resistance it will dissipate some of the power. ते काय करेल, काहीतरी power dissipate करेल. So see, generally the brushes are assumed to have a constant voltage drop across them. So generally we can assume that the brushes is having an constant drop. Brushes it is having a constant voltage drop. Generally we can consider a 2-volt voltage for graphite brush and 0.5 volt voltage for a metal graphite brush. So all of you note down this value because it is somewhat used in the MCQ, or it may be asked in the MCQ. So see, generally in the brushes we assumed the sum of the constant voltage drop. That means we have assumed some constant voltage drop. We minus this drop from the supply voltage, and this is generally for 2 volt for graphite brush, and it is 0.5 volt for a metal graphite brush. Metal graphite brush साठी ते 0.5 असेल आणि for graphite brush it is nothing but 2 volt. Okay, so this is the brush losses. Again there is some of the losses it will be occur. Now see, the mechanical losses. In case of mechanical losses, the mechanical or friction and windage loss are due to the friction in the bearing and the energy that is dissipated in the turning that the rotor through the ear inside the machine. Okay, see the mechanical losses, as we know that the rotating part it will be present in case of DC motor. So there is a some of the rotational losses like a mechanical losses. Okay, see, in case of mechanical losses, the friction and windage loss it will be occur. So this friction loss due to the friction between the rotation part and the one of the stationary part. So do you know that the shaft of the motor it will be fixed on the one casing, and it is in between the stator it will be start rotating. So at that situation it will be rotating in between the flux fixed part. So flex for the smooth rotation we required one of the bearing. आपण एक bearing टाकतो. If the bearing it will be rough, then the friction it will be more. If the bearing it will be smooth, then the friction it will be less. And somewhat if the bearing it can be damaged, or it may be somewhat bearing it can be broken. At that situation it will affect on noise also. So noise it may be increases. त्याचा noise पण काय होतो, increase होतो. And the energy that is dissipated in the turning the rotor through the ear inside the machine. Okay, so see the energy which is required to turn the motor at the time of starting through ear. So there is some ear gap between the stator and rotor. So at that situation, in between that somewhat bubbles it will be formed, or it may be somewhat ear gap. We can call it as a stray losses. The rotational losses can be determined by driving the machine at rated speed with no load or excitation. How the rotational losses it can be calculated? So see, the rotational losses it can be calculated or determined by driving the machine at rated speed. Okay, machine वरती load न देता at no load condition or at not excitation it can be provided. At that situation we are just running the machine and we are calculating the no load losses like rotational losses. Okay, so rotational losses are frequently lumped with core loss and determined at the same time. So जे काय आपण core loss calculate करताना आपण no load test conduct करतो. So while conducting a no load test, this is lumped with, that means rotational losses, it can be lumped with that core loss, so that these losses, that is rotational losses, it can be calculated while we are calculating the core losses. ज्यावेळेस आपण core losses calculate करतोय, at that situation we are calculating, or at the same time we are calculating the rotational losses. So these are the mechanical losses. After that, core losses is there. So core losses, it is called as no load losses, or we can call it as a open circuit losses are also there. So open circuit losses, or it may be core losses, rotational losses, or it may be core losses. So this rotational losses, or it may be core losses. In case of core loss or rotational loss, in case of core loss, or it may be rotational loss, these losses, it can be calculated at the no load condition. Similar to that of mechanical losses is also called calculated at the no load condition. So see, the core loss, it can be divided into again two types, that is hysteresis loss and eddy current loss. So it is measured at no load condition, and the combination of these two losses we can call it as a core loss with the mechanical losses constitute the no load rotational losses. It will constitute no load rotational losses. It will constitute a no load rotational losses. So see, it should be noted that distortion of the field such as by armature reaction may significantly increase the core loss. Okay, see, if there is a distortion in the field, or it may be distortion in the flux due to the armature reaction, you know armature reaction effect. If due to the armature reaction, it will having an two effect. One is effect is nothing but it will distort the main field winding, or it may be it will weaken the main field winding. If such a distortion, it will be occur in case of such a distortion, it will be occur due to that armature reaction by the main flux, then the losses, it will be changed. हे जे काय losses असतील ते core losses काय होतील, change होतील. Such by armature reaction may significantly increase the core loss. Okay, see, if the distortion, it will be occur, ज्यावेळेस distortion occur will, when the distortion, it will be occur, then the flux distortion, it will be occur, and due to that flux distortion, the core losses of the machine, it will be changed, that is core losses of the machine, it will be increases. Okay, so the difference between the measured and actual core loss is put in the stray loss category. So the difference between the measured and actual core loss, measured value and actual core loss च्या value मधला जो काय difference असेल, it is put in the category of stray losses. Stray losses च्या category मध्ये आपण काय करतो, put करतो. Okay, so this is comes under no load loss, or it may be mechanical losses. So these are the rotational type of losses. Now see the stray losses. So in case of stray losses, generally we can consider the stray losses, it is nothing but it is the 1% of the output of the DC machine upon DC generator. In the case of DC generator, we have already discussed regarding that. By convention, stray load loss are considered to be 1% of the rated output for the DC machine. DC machine जे काय rated output असेल त्याच्या 1% losses हे stray losses we are considering. Okay, see, so this is related to that of losses, copper loss, then mechanical losses in case of friction and windage loss, and the core loss in that hysteresis and eddy current loss. And again we have discussed regarding stray losses. Okay, so these are the losses of a DC machine. DC machine चे काय झाले हे losses आहे. Now we will discuss regarding efficiency of the DC motor. Efficiency of the DC motor. Okay, see, Can anyone tell me the formula for efficiency? What is the definition of efficiency? We have already discussed in case of DC generator. Definition of efficiency.
Ratio of output upon ratio of the input.
It is the
Ratio of the output to the input.
ratio of output power to the input power. It is nothing but it is the efficiency. Output power and input power चा जो काही ratio आहे, so this ratio, it is nothing but we can call it as a efficiency of the machine. So we can call it as the efficiency of the machine. So see, in case of efficiency of the machine, we know that the supply voltage of the motor, it is nothing but V volt. मोटरला आपण सप्लाय देतोय, so supply voltage of the motor, it is nothing but V volt. So if the supply voltage of the motor, it is nothing but V volt, it will draws a sum of the current, that is I amount of current from the mains of the supply during its running, or it may be while its operation, it will be going on. So the input power of the motor ची जी काय input power, formula for power is nothing but supply voltage V into current taken from the supply, that is I. It is nothing but input power, that is P in is equals to V into I. That is input power of the motor, it is nothing but V into I. Okay, now according to power stages, there are some of the copper losses between the supply to that armature of the machine. Machine च्या armature पासून supply पर्यंत मध्ये काय आहेत copper loss आहे. So if the copper loss, it will be present in between that, and then the mechanical power, it will be developed in the armature. So this mechanical power developed, PM is equals to EB into IA, that is value of back EMF and the armature current, that is EB into IA. It is nothing but mechanical power developed in case of machine. And if after the mechanical losses like a friction and windage loss, we will got the actual output, or we will got the actual power output of the machine. We will got the actual power output of the machine. So this power output, it will be obtained when this mechanical losses or the core losses, it can be subtracted. So if we consider these core losses and the mechanical losses in the constant losses term, so that we can minus WC, that is constant losses of the motor, from the mechanical power developed in the armature, then we will get the actual output power. See, so see, if we consider input power is nothing but V into I. Again, if we consider the losses, that is copper loss IA square RA minus again WC is nothing but we get the output power, that is P out. Okay, see here WC is nothing but constant iron loss in the machine. So the approximate power equation of the machine, so this is the power equation. All of you write down this power equation, all equation write down, because it is useful while solving the problem. ज्यावेळेस आपण प्रॉब्लेम सॉल्व करतोय त्यावेळेस इट इज युजफुल, it is useful while solving a problem. That is the input power, then power developed in the armature EB into IA. P out is nothing but output power, so it is equals to PM minus WC, and where WC is nothing but constant iron loss in the machine, constant iron loss in the machine. Okay, so see, so the approximate power power equation, that is P out, output power, input minus losses, so input power V into I minus losses, that is copper loss, we can represent it is PCU, and WC is nothing but constant loss. But there are two losses that we have not considered for the simplicity. Just 1 minute. Okay, see the power equation, that is approximate power equation we got. Output power, it is equals to input power minus losses. So P out, it is nothing but output power we can get at the shaft of the machine. Input power is nothing but V into I, that is supply power, supply voltage and the supply current, V into I. After that we calculated the copper losses, that is I square R, and WC is nothing but constant losses. WC, it is nothing but constant losses. Okay, see, for our simplicity we have not considered other two losses like copper losses which are occurring in the field winding. फील्ड वाइंडिंग मध्ये ऑकर झालेले लॉसेस आपण कन्सिडर केलेले नाही तिथं. सो सी द लॉसेस विच आर ऑकर इन द फील्ड वाइंडिंग लाईक कॉपर लॉस in the shunt field winding. If there are series field winding, then the copper loss in the series field winding. For series connected motor or for the series motor, the copper losses it will be occur in the series field winding, and in case of shunt field winding, the copper losses it will be occur in the shunt field winding. We have not considered for simplicity or for representing the formula of power equation. Okay, so this is the power equation related to DC motor. To it is useful while calculating the efficiency. See, according to this equation, we are able to define the formula for efficiency, and we are able to define the type of efficiency. So do you know that there are three types of efficiency? First one is nothing but efficiency we have calculated in case of DC generator also. In case of first one efficiency is nothing but overall efficiency. Second one is nothing but electrical efficiency, and third one is nothing but mechanical efficiency. Electrical efficiency, mechanical efficiency, and the overall efficiency of the DC motor. DC motor ची overall efficiency. See, overall efficiency of the DC motor is nothing but overall output power or the final output power which are obtained divided by input power. So if I draw the phasor if I draw the power stages here, and if I have given the name on that power stages, suppose this one is the first one power stages, that is A, it is nothing but electrical power. So it is the input of the motor or P in. After that there is a sum of the copper loss, that is I square R loss, and here it is B stage of the power is nothing but mechanical power developed in the armature, or we can call it as a PM. Okay, see, after that we got the actual output of the motor or output power. If we represent, this is P out, it is nothing but power stage C. Okay, C power stage. See, if we calculate the overall efficiency, if I calculating overall efficiency, then we are able to calculate the actual output divided by input power. That means we take the ratio of actual output divided by power input. So that means C divided by A. C divided by A is nothing but overall efficiency. See, the overall efficiency of the DC motor, it is the ratio of output power to the input power of the motor. Output power to the input power of the motor. We also call it as a commercial efficiency. त्यालाच आपण commercial efficiency we can call. See, NC, that is overall efficiency or the commercial efficiency, it is equals to it is not a NC, it is eta C. It is equals to P out divided by P in. It is equals to VI minus IA square RA minus WC divided by VI. See, P input काय आहे? It is nothing but input power. P out काय आहे? आपण आताच कॅल्क्युलेट केलं किंवा पॉवर इक्वेशन राईट केलं. Input power minus losses. Which are losses? That is copper loss and constant loss. So VI minus IA square RA minus WC. Okay, so this is the formula for commercial efficiency. Now, if we calculating the electrical efficiency, while calculating electrical efficiency, electrical power developed in the armature, that is B stage, it is the output in that case, and power input, it is nothing but input in that case. So B divided by A. B divided by A is nothing but PM divided by P in. power developed in the armature of the motor divided by input power. It is nothing but it is the electrical efficiency. This is nothing but electrical efficiency. Okay, that is EB into IA is the power developed in the armature divided by V into I. It is nothing but input power fed to the top machine. Machine la dileli input power, right? No. So these are the electrical efficiency. So this is the ratio of armature power to the electrical input power. Then the mechanical efficiency. Next one, the mechanical efficiency is nothing but it is the ratio of actual mechanical output divided by power developed in the armature. Power developed in the armature. So it is nothing but it is the ratio of C divided by B. C आणि B चा काय असेल तो ratio असेल. So if it is the ratio of C divided by B, then we can get the equation or the efficiency formula, that is mechanical efficiency. Efficiency mechanical is equals to P out divided by PM, where PM is nothing but EB into IA, and you people know the PI is nothing but VI minus IA square RA minus WC. IA square IA square RA minus WC. Okay, so this is the output power divided by PM is nothing but EB into IA. EB into IA, it is nothing but input power. Okay, it is nothing but input power. Okay, so this is the formula for mechanical efficiency. If we solve this formula, or we just get simplification of that equation, after that we got this equation VI minus IA square RA minus WC. Again we know that EB into IA, that is PM is equals to VI minus IA square RA. आपण पाठीमागे derive केले, that is input power minus copper loss is nothing but power developed in the armature, that is EB into IA. The same in, so if we divide, then we got this equation efficiency mechanical is equals to VI minus IA square RA minus WC, minus IA square RA minus WC. Okay, getting, this is the some of the formula for efficiency. I think all of you getting this. Getting no?
Sir.
Okay, see, all of you getting no? This all three formula for efficiency.
Yes, sir.
See, now we will derive the next one point is that condition for maximum efficiency. So it is very easy. We want to derive that condition for maximum efficiency. I will write here also. See, as we know that we have derived the equation, we have already derived the equation, that is power output and power input. Output power and input power से equation आपण already derive केले. Also we have know the equation of commercial efficiency. What is the formula for commercial efficiency or overall efficiency? Eta C, it is equals to P output, actual output power, P out divided by P in. So do you know that efficiency C, it is equals to P out, input power minus IA square RA minus constant losses WC divided by V into I. Okay, right now, see, this is the equation, that is commercial efficiency. If we neglect the shunt field winding current, instead of representing I, we are representing IA, and then we got the equation commercial efficiency. It is equals to VIA minus IA square RA minus WC divided by V into IA. Now see, divide this V into IA separately on this term. या टर्मला separately divide करा V into IA ना. So this is nothing but efficiency C. It is nothing but V into IA divided by V into IA. किती येईल? Minus IA square RA divided by V into IA plus WC divided by V into IA. Right? No? बघा हा जो काय VA आहे त्या सेपरेट टर्मला डिवाइड केला, या टर्मला डिवाइड केलं V into IA येईल, मायनस कॉमन घेतलं, याच्यामधून ब्रॅकेट मध्ये काय राहील IA square RA divided by VIA minus WC divided by VIA. This VIA get cancel. We got equation 1 minus याचे डिवाइडेशन घेतलं की याच्यामध्ये 1 येईल. सो 1 minus IA square RA divided by VIA. याच्यामधला एक IA याच्यामधला एक IA get cancel. So it is nothing but remaining term is nothing but IA into RA divided by V plus WC divided by VIA. WC divided by V into IA. Right now? See, this is one equation we have derived. See equation आले बघा 1 minus IARA divided by V plus WC divided by V into I. Now efficiency it will be get maximum. Efficiency कधी maximum मिळेल? Maximum म्हणजे कशा, याला जर multiply by मी 100 केलं, okay, if this value it will be 0. 1 minus 0 किती येईल? 1, right? No, into 100 it is nothing but we achieve 100% efficiency. कधी जर ही जी काय टर्म आहे that is IARA divided by V plus WC divided by VIA if it is 0. ज्यावेळेस ती टर्म त्या टर्मची व्हॅल्यू 0 असेल then we will get the efficiency maximum. Okay, now we will check at what condition this term it will become 0. So for that, see, now the efficiency is maximum when the term under bracket in the above expression, या expression मधली ही काय bracket मधली term आहे, if it is 0, again this condition is satisfied. So that if we differentiate this above term, जर ही term मी differentiate केली, differentiation of this term with respect to IA, d upon dIA, that is IA divided by RA divided V plus WC divided by VIA, it is equal to 0. ज्यावेळेस ही टर्म 0 येईल त्यावेळेस माझी इफिशियन्सी काय येईल? मॅक्सिमम येईल. सो आय वांट टू कॅल्क्युलेट द कंडिशन. मला ती कंडिशन कॅल्क्युलेट करायची आहे, कोणत्या कंडिशनला इफिशियन्सी मॅक्सिमम मिळेल. सो सी, वी वांट टू टेक डिफरन्शिएशन. सो ऑल ऑफ यू डिफरन्शिएट दिस इक्वेशन. Do the differentiation with respect to IA. First of all, do first term, secondly second term. Differentiation of IA RA divided by V with respect to IA. Kyle, I will write here. Differentiation of IA into RA divided by V with respect to IA. IA RA divided by V is a differentiation with respect to IA. Kyle,
RA upon V.
RA upon V. That means differentiation of IA with respect to IA is nothing but 1 yield. So remaining term as it is, that means RA divided by V plus next one WC divided by V into IA. Differentiation of this term with respect to IA. WC it is constant, divided by V is constant. 1 upon IA is a differentiation with respect to IA. Kyle, 1 upon IA च differentiation with respect to IA. 1 upon x च differentiation with respect to x काय असतं?
1 upon x square.
1 प्लस का मायनस पण? 1 upon x च differentiation with respect to x minus 1 upon x square असतं का plus 1 upon x square? Just check the formula. differentiation चे. So it is nothing but minus 1 upon x square, that is minus 1 upon ia square. मॅडम 2 मिनिटात कॉल करते तुम्हाला, लेक्चर मध्येच आहे मी. हां, दुसरं लेक्चर टाकले आता तुम्हाला मी सांगतो मी. Okay, see, RA divided by V plus WC divided by V minus 1 upon IA square, हे differentiation वाला is equals to 0. So equation becomes RA upon V minus WC divided by V into IA square, it is equals to 0. So see, shift this term to the right hand side. Equation becomes RA divided by V is equals to WC divided by V into IA square. This V get cancel. Remaining term हा IA जो आहे तो लेफ्ट हँड साइडला शिफ्ट केला. This becomes IA becomes IA square into RA is equals to WC. So this is the condition we obtain. IA square RA is equals to WC. What is IA square RA? What is IA square RA? Which loss? Copper loss. And WC is nothing but constant loss, right? No. So see, we get the maximum efficiency when the condition it will be obtained like copper loss is equals to core loss, or it may be copper loss is equals to constant loss, or we can call it as a variable losses. It is equals to constant losses. Then we will get the maximum efficiency. त्यावेळेस आपण मॅक्सिमम इफिशियन्सी काय होते मिळते. ओके, गेटिंग ऑल ऑफ यू अंडरस्टूड दिस लिटल बिट डेरिवेशन, स्मॉल वन. लक्षात आलं का? ऑल ऑफ यू गेटिंग? नो, गिव मी रिस्पॉन्स इमिडिएटली.
Yes, sir.
Okay, so see, in this way we will conclude this today's lecture and we will stop here. Just 1 minute.